So my name is Vasilis Mazaris. I'm with the Information Technologies Institute of the Center for Research and Technology, Hellas. And as my affiliation suggests, what I'm presenting will not be about biology, so it's on the ICT side. It continues in the stream of AI-related presentations that were included in this day. And what I will be presenting is actually in two parts: a system that we have built for individuals, for supporting individuals with intellectual disability, which is something more generic, of course, than the Cliffstra syndrome. And then the second part, I will present some more video and image analysis techniques, which we have developed in my lab, which are not applied to content that is, again, specific to the Cliffstra syndrome, but still could have some related applications. And I hope that this presentation can provide some hints on what can be done with this kind of techniques. So the QualiSID system is part of a project that aims to develop a fully functional, user-friendly, interactive support system tailored to the needs of people with intellectual disability. QualiSID is a project that is co-funded by the European Union and by Greek national funds, as shown on this slide. And this system has three main components. It is a web-based user interface for recommending entertainment and educational content, audiovisual and textual content for entertainment and education. So this part is basically a recommendation system. Then it has a second component which relates to the detection of emergency situations and automated assistance. This uses wearables and smartphones for supporting such individuals, monitoring specific biosignals and the like. And then there are other smartphone services. And we have an early overview of this system in the publication that is shown on the slide. So, starting with the QualiSID objectives of the first part of the system, which is the web-based user interface. This is about providing recommendations for content. So it's an easy, simplistic, I would say, user interface that allows individuals with intellectual disability to navigate through content, get recommendations of content based on their preferences. And this involves capturing the preferences, of course, and understanding also what the content is about so that we can recommend content that is related to these preferences. In terms of detection of emergency situations and automated assistance, we're monitoring critical biosignals such as heart rate, oxygen saturation, body temperature, using wearable sensors. And we're also using GPS from the smartphone to detect wandering behavior, detect disorientation, detect if a person is wandering outside certain region. And we have the possibility to have automated system alerts if some of these signals go off the expected values, and also a call for help functionality for the individual to issue an alert if he feels or he or she feels distressed. And the third component, which is other smartphone services, this involves phone communication through voice commands and speech recognition, so easier to use communication. Entertainment functionalities, again, with a virtual assistant and recommendation of content. And then also the support of caregivers and relatives of individuals with intellectual disability by sending them reminders for reminder medication or for any other situation that is captured by the sensors. So going back to the web-based user interface, this is the only one of the three parts of the QualiSID system that I will be presenting in more detail today. This revolves around certain content categories. So in order to make recommendations of content to these individuals, we have to, on the one hand side, understand what their preferences are. So do they want entertainment content or informational content? If it is entertainment content, which are the categories that are more or less interesting for every individual. And similarly, we have to analyze the content to understand what the content is about and be able to make meaningful recommendations of content to individuals. And for this, we have a user profile that is based on a certain number of categories that we have identified in collaboration with relevant caregivers and institutions that support individuals with intellectual disability. So this is a rather broad spectrum of potential categories that could be of relevance, of interest to someone. And then we also make a user profile, which means that we can capture the preferences of each individual user. And this involves an initialization of the profile, which is done typically with the help of a caregiver. So we do not expect an individual with intellectual disability to do this manual step. But then this update of the profile is done in a fully automatic way. So looking at what content they have been consuming, understanding based on this consumption pattern, what more content would be relevant to them. So this doesn't involve any interaction with the user anymore, doesn't require any interaction with the user. And this is what this very simplistic user interface looks like for a recommendation system. So it has a login page, of course. And then if you go to trying to consume some content, looking for some content, you get presented with some initial functionalities and categories of content. And going, for instance, for the selecting the news category, you get some subcategories of these. So you can easily navigate with some photos and some graphics. You can navigate to different categories. And then a different individual comes and it gets a new set of categories that is based on his preferences. So again, selecting entertainment here, you get some more subcategories of entertainment, and you can easily navigate through content. And hitting one of these categories means that you get a list of recommended content that belongs to this category, which can be coming from different sources. It can be local content, it can be from the web, and this is relevant content to this category. But also then, by use of the system and understanding the more specific preferences of the user, for the same category, you get different, more tailored to you set of content after using the system. So this kind of recommendation evolves as the user interacts with the system, and we can understand better his or her preferences. And similarly for some other category, this is paintings, and then you get some different results based on the use of the system. And you can also sort them by different types, so then you can separately get the different types of multimedia content that we can recommend. So that was about the Qualicid system. Just the first part of the system, as I mentioned, the web user interface that serves as a recommendation system. I didn't touch here on the smartphone wearable functionalities. This takes us to the second part of my presentation, which has to do with AI techniques and how we can analyze multimedia content to understand what it is about. So this is relevant for the Qualicid system. Some of these techniques are used as part of the background of the system to analyze the content, to understand what it is about so that we can recommend it. But also these are quite generic techniques that are applicable to several other domains. The media domain, for instance, for organizing content of audiovisual archives. And they are more generic AI techniques as well that can be applicable not only to generic content, so videos and images, natural videos and images, as we have in this application, but possibly also to content that is more relevant to the biomedical domain. So we will look into this kind of techniques. And some of these techniques come from the Qualicid system, so Qualicid project, so they were developed in this. Others are just used in Qualicid, but were developed in other projects, including the Criteria and AI for Media H2020 projects. So I will present three types of techniques here. The first has to do with video event recognition. So the goal here is, given a video, to actually understand automatically what the video is about, just like we as humans can see a video and understand what it is about. So what we do here is we perform an in-depth analysis of the video. We detect objects, we understand the interactions between the objects and how these relate. So we end up with being able to automatically annotate this video with the event that is shown, the event that is taking place there. And this is done through a quite complex deep network that processes the videos and produces the annotations. What I would like to stress here is that we do not use any textual metadata. So we just take the video, just like a human will watch a video without having additional knowledge about what this video is about, and we understand what it shows. And why this is potentially relevant here, because this kind of techniques could also be applicable to video content that observes patients in their daily activities, for instance, and can try to give us hints on how they behave or how their behavior differs from that of a non-patient. So the video is the input, the understanding of what happens in the video is the output. And we can also explain why this output, why the network has reached this decision. So this is another big issue that has been mentioned a couple of times today, the explainability of AI techniques. So this is, of course, an explainability approach that is very much tailored to video analysis. It's not a very generic technique, but this is how we can explain. So we can pinpoint specific frames within a video and specific objects within the frame that led the classifier to make a decision, to say that this video is showing a person cleaning his car from snow, for instance. So this kind of techniques, although they seem quite divergent from the main topic of the conference, I think they can be applicable also to content that comes from observing individuals and can also give us hints on why then a classifier decided that this or the other behavior is not exactly the anticipated one, not what we expected. So the other thing, the second technique has to do with free text video search. So this is relates somewhat to what was presented in the previous talk about understanding what research articles are about and finding relevant content. But then this is the analogous for video. So we can automatically understand what the video is about and associate it with a textual query. So you can type, I'm looking for a video showing this and this and that, and you get the results that the videos that show what you're looking for. And this is in a very, very high level how it works. So we can represent both the videos and a textual content in the same feature space, as if they were of the exact same modality, not two different modalities. And this means that we can associate textual content with videos and retrieve the relevant content. And this is what it can look like for typing a DJ playing music, and you get this kind of results as output. Again, here without having any metadata for the video. So we don't have text that comes with the videos that we process. We just look at what the video contains as a visual content, just like a human would do. And similarly for a group of people kayaking. So this is relevant for the Qualicid system because it supports the search and recommendation functionalities. It helps us to retrieve relevant content. And it could also be applicable to observational data as well for typing in what you are looking for, what kind of activity you're looking for within a large collection of videos, and retrieving this specific content that you're looking for. And the last technique is about explainable deep learning. So I showed in the video analysis, the event recognition part, that we have some explainability aspects included in this technique. So here, this is another technique that has to do with the classification of images. And what we can do here is given an image classifier, which in our case works with generic content, of course, and classifies it into generic non-medicine related categories, we can understand in which parts of the image the classifier was focusing on to make its classification decision. So we can go back and detect, for instance, biases in the classifier, where the classifier might have made a right decision, but looking at the wrong part of the image. So actually, we have a biased classifier. So these are some examples where we can see the natural images that we are working with, and the heat maps show different types of explanations that we can generate for the decisions of the classifiers. And we can see, for instance, that this is an example of bias. Looking at the sunglasses images, so these images were ground truth annotated as sunglasses, and they were in some cases detected as sunglasses. But the classifier actually looks at the entire face to make this decision. So looking at more images, and images also of sunglasses that are just left on a table, are not worn by a person, which are misclassified, we can understand that actually the classifier has learned a different concept. It has learned to detect faces wearing sunglasses, not just sunglasses. So this is an example of a biased classifier, which again, this is not in a medical application, but similarly, you can have, as we saw already, needs to classify images to make decisions, to help the physicians. But again, you need to be also certain of whether the classifier is making the right or the wrong decision, and if it's making whatever decision, where the classifier is based on to make its decision. Is it a well-trained classifier, or is it a biased one? And similarly, you can see some more examples. These are on the right-hand side. It's the examples of images with sunglasses left on a table, so which are misclassified. And some more examples here of different classifications for the same image, and the parts of the image that the classifier looked at to make the different decisions. So for making different decisions, the classifier looked at different parts of the image. So again, this is a technique that can be applicable to classifiers of images to help verify that the classifiers are not biased. So this is all from my side. The presentation and the topic of it was quite divergent from the rest of the conference, but I hope it was interesting, and maybe this kind of visual analysis can inspire some similar applications of visual analysis in your domain. Thank you.